Good day, everyone. Welcome to FIT3143 Parallel Computing. We are into week 12 of the semester, and today's lecture will represent the last lecture for this unit. And in today's lecture, we will be discussing a new topic, a new platform on how you can further expand parallel computing into a different hardware. But this particular lecture topic in week 12 will not be covered in your exam. All right, I think they've made it very clear in Moodle also that today's lecture on introduction to GPU computing for general purpose computing, also known as GPGPU. It's something of an add-on knowledge for you all, and to give you a much more better exposure of how we can expand parallel computing into different architectures to further improve data parallelism. So today's one is focusing more on data parallelism using GPUs. And after this topic, then I will use the remaining time just to do a very brief review of our lectures since from week 1 to week 11. So the content of your lectures, labs, tutorials, and assignments which you have undertaken from week 1 to week 11, that content will be, not all of them, but a portion of them will appear in your final exam. Okay, so moving forward, so let me stop sharing my video, and then I will share the screen to go into the lecture slides. Okay. Okay, so I'm sharing my screen just to do a quick test. Can you all see the shared screen? Guys and girls, can you all see the shared screen? Okay, good. Okay, good, Daniel. Thanks, Emily. All right, so in here, before I go, I just want to recap again. So in week 12, we'll be discussing graphics processing unit, whereby I will introduce you to the idea of compute unified device architecture for general purpose computing on GPU. And then we will go a bit into CUDA and C programming language. So if I were to cover all 3 lectures, I think probably we will eat into 2 hours. All right, but I plan to reserve at least half now to talk about the revision and final exam details. So I'll try to complete this within an hour and so. All right, I think it can be quite fast depending on how much time I should. Because I plan to show you a quick demo also on how you can actually write a parallel. How you can write a code to carry out a parallel computing task on a GPU. All right. Okay, then after that, we will conclude our lecture today with some brief revision lecture notes, and then I will give you some details about the final exam. All right. Bear in mind, actually, the tutorials I haven't updated yet. Actually, this week's tutorial will be going on tomorrow. And based on your respective tutorial schedules. It's just that it's going to be mostly a revision-based tutorial, and we'll just cover some very basic questions about MIMD. There's no more tutorial quizzes. Week 11's tutorial quiz was the last one. I've reopened it based on requests received by several students because they were focused on the assignment and they didn't have time to do the tutorial quizzes. So I said for week 11, so I said, okay, we open it one more day. Labs, there are no labs exercises in week 12, but we will use week 12's labs to conduct the assignment, software demonstration, and Q&A interview. So for the Malaysian cohort, we will send you all a message to give you all your time slots, just like what we did in assignment 1. Okay, you should get a notification by tomorrow. All right, for the Clayton cohort, I think your tutors would be in touch with you all, and you can actually please attend the labs to actually demonstrate your software and to answer questions by your tutors. All right. And again, guys and girls, please complete the Cert 2 for this unit. You click on this unit, it will bring you to the Cert 2. It is very important for us, for the teaching team. We have undertaken substantial improvements over last year's offerings, especially in the way we revamped the labs and also the assignments. Okay, and we hope the lectures also, we have made some changes. Of course, we have introduced a new lecture topic on POSIX threads. We've also introduced a new lecture topic on SIMDs, and also today we are discussing a new lecture topic on GPGPUs, although this topic will not appear in your exam. All right. So I hope all of the improvements that we have done last year, of course, I mean, almost all of you all are doing this unit for the first time. So at least what we hope is that at least the changes made would have improved your learning experience of this unit. And please provide your feedback on what you liked about this unit and what you feel can be further improved in this unit in the CERT2 evaluation. It is very important to the teaching staff. So I hope you can complete this, especially when, especially your input on your overall satisfaction of the unit is extremely important to us. So please, I hope you can spend a few minutes to complete this particular CERT2 assessment. All right. Okay. So now going to the, just to let you all know, at this point of time, the response rate, I checked last night, the response rate for Clayton, I think, is less than 10%. And the response rate for Malaysia is about 13%. So, I mean, it's low. We really hope to get a much more higher response rate. We are hoping at least to break the 50% response rate, which means that we hope at least half or more of the class in Malaysian cohort and half or more of the class at the Clayton cohort will participate in the CERT2. So this is something we're really imploring you all to please complete the CERT2 for this unit. Okay, it's just a few minutes of your time and it really means a lot to us. Thank you very much. Okay, so going back to the lecture notes of today, I think I spent quite a lot of time on this already. Okay, so in today's lecture, let's have some fun. All right, so in today's lecture, sit back. Okay, it's not going to appear in the exam, so no need to worry too much about really trying to remember or practice the lecture. But I hope, based on your interest that you develop in parallel computing, you would get a much more better understanding. So today's lectures, the slides of today in part A, part B, part C, were actually taken from other sources. That's why we decided not to put the Monash University logo inside here. I mean, that would not be appropriate. So the first slides here are from Sang Woo from University of California, Irvine. I think he made his slides publicly available, and I thought the content is quite well done. And yes, and will definitely give you some exposure to the unique content. Okay, so let me repeat again. The contents of week 12A, B, and C on GPU computing will not appear in your exam. All right, as we have mentioned inside here already. All right, week's 12 lecture content on introduction to GPU and CUDA will not appear in the final exam. This is just provided to expand your horizon on parallel computing and GPUs. The reason why we can't test you is because we don't have a lab. To actually do this, you actually need a GPU card. Of course, we can use Collab, but I thought, okay, never mind. We will just introduce this as your own knowledge, and we hope that you will actually pick it up on your own. For those of you who plan to expand parallel computing in your career or in your academic research, should you pursue in the direction. Okay. All right. So going back to here now. When we talk about graphics processing, all right, okay, graphics processing, I'm sure all of you all would have played computer games, all right. So I hope again, this session is being recorded, so you, by all means, you can always mute your microphones and raise your questions on the Zoom group chat. But given that this is the last lecture, I really hope you all can speak up a bit. There's no wrong questions or anything like that, all right. So I'm sure all of you all are active gamers, correct or not? Okay, I'm sure all of you all are active gamers. Do you all do gaming? Anyone here? I mean, do you all do gaming? How many of you all do gaming? Can you all say? Maybe I should do a poll. Just give me a second for a while. I I know I've gotten feedback to do Flux, and I've not been very active on Flux. Okay, okay, do you actively game on PC or console? Okay, all right, let me just put this. All right, then let me just move this up. Okay, so so today's, if you all are familiar with Flux, you all can just go to Flux. I've put the Flux notification here already. You can click on it. All right, I'm going to present this now. Okay, so I think I think you all should be able to participate in this. start. Okay, so I want to share my screen again. Okay, yeah. So the flux is okay. So I see 2 responses. 2 people have answered. Anyone want to answer more? 4 people have answered. Just click on the flux link I shared to you all, and then just do you actively game on PC or console? So 5 people have answered. I mean, this is a very icebreaker session only. Nothing. Okay. So I can see. So not bad. Not many. Okay, we can see more gamers now. I think this indicates all right. Okay, so all right. So I think I'll just stop this in 5 seconds. 4, 3, 2, 1, 0. Okay. So I mean, this is a simple icebreaker over here. Not, again, today's lecture, I'm taking it easy, free and easy a bit. So at least that you all can, at least we can end on a much more happier note. All right, no other option. Okay. So as you know, when you do gaming, all right, especially those of you all who are active gamers today, what is important other than CPU in game? You need a good GPU, a graphics processing unit. All right. So the purpose of the graphics processing unit, as the name implies here, is to do the 3D processing, is to do the computationally intensive 3D processing. So whatever, so the CPU does most of the decision algorithms, the logic based on the game AI and so forth. But when it comes to rendering the graphics, so when you guys play Call of Duty, Modern Warfare, or the Formula One Forza games, or my God, I can't, or what Lara Croft, Tomb Raider, and things like that. All right, so you can notice that, you know, or when you all watch tech reviews, when they look about, when they're reviewing the latest graphics cards from Nvidia or AMD, what they're looking for, they're looking at frame rate. So those graphics cards, the faster they can render the images to screen, of course you also need a high refresh rate monitor, then the better the card is being perceived. All right, and generally that's how graphics processor has been in its history. All right, so in the past, okay, the CPU back in the 90s, before you had 3D accelerators, okay, the CPU had to do most of the texture mapping and so forth. All right, then as you can see, you know, so the CPU had to do most of the graphics computation while maintaining a good frame rate. So these are some of the old days programming, when you play Quake 2, Quake 3, and things like that, first person shooting games. All right, okay, then when 3D accelerator cards came about in the late 90s and the early 2000s, okay, back then they had a Voodoo chipset. You know, when I was a kid, we were all mesmerized by this kind of cards. You know, S3 or Nvidia Voodoo chipsets and things like that. All right, so where they had 3D FX processors inside here. Yeah, this is literally ancient guys. You know, and you can see this is using a 3D dedicated. So this is one of the earliest GPU cards, a dedicated GPU card. Okay, they plugged it into your PC and then they connect to your display, and then they actually had 3D rendering, 3D effects that allows you to do 3D acceleration. So you can see the quality of your game significantly improve from highly pixelated to something much more smoother, and the frame rate also increases significantly. I mean, or at least they maintain the frame rate back then. All right, okay. So from here, GPU cards have evolved so much. Okay, this is the earlier days GPU cards. These are all the RAMs, you know. Okay, these are all the RAMs, and you'll be lucky if this is like maybe probably 2 megabytes. So this is total 8 megabyte GPU RAM. This is probably 8 megabyte GPU RAM, if I'm not mistaken. All right, and in today's cards, if you were to go and buy off the shelf Nvidia GeForce RTX 3090, has 20 gigabytes of graphics memory. Or if you go and buy the latest AMD Ryzen, I'm sorry, AMD GPUs, the 6950, forgotten already, just came out a few days ago, that runs on 16 gigabytes of GPU memory. So you can see over the past 20 years, there have been a huge leaps and improvements of GPU technology for graphics. And if you look at a GPU card contains thousands of small cores. Okay, thousands of small cores. Each core contains an arithmetic logic unit that is focuses on performing 3D raster operation. 3D raster operation. Of course, they have a cache memory and things like that. But if you look at the layout of a graphics processor in general, they contain thousands, hundreds or thousands of small cores, very, very small, lightweight cores. Okay, when you compare this, to let's say, when you compare this to let's say wait, my apologies. When you compare this to, let's say, a CPU core, so as you can see over here, this is an Intel Core CPU core. You have 4 cores. Each core has a very complex instructions. They're based on the CISC architecture, CISC, complex instruction set. Forgotten what the C4 already, but anyway. So, but these are complex based architectures, which means that these cores, it contains instruction sets that allow you to write operating systems on top of them. Okay, so and then they can perform complex instructions. They can also perform scientific operations and so forth inside here. But when you compare this to the right hand side on a GPU card, okay, although we don't have the actual microscopic image of it, but if you look, actually it contains hundreds or thousands of cores. Each core is very light. It only contains an arithmetic logical unit to perform arithmetic based operations. Okay, arithmetic based operations, mostly for geometric or 3D based object rendering operations over here. So that is how a GPU card has been generally the idea of it. Now, what happened was, okay, in the year 2006 or 2007, okay, Nvidia was one of the first, thought, okay, all the while most of the scientific computations were being carried out on CPUs, and most of the graphics rendering operations were carried out using a GPU. Now, why not I use since my GPU has thousands of cores, hundreds of thousands of cores, why not I I repackage, don't say modify. They didn't modify a GPU hardware, but let's say I come up with a software library that allows me to perform general purpose. So no longer graphics operations, general purpose computation on a GPU. Okay, so like let's say computations which can be embarrassingly paralyzed, like matrix multiplication, vector operations, like you learn SIMD in week 10. Those kind of operations, you paralyze them on a GPU card, but you provide a framework or a library for users to actually access the GPU cards. And from there, we can see, since 2006, okay, from 2006 2007, okay, when CUDA was first, this is the time when CUDA was first announced. CUDA stands for compute unified device architecture. Until 2020, or 2020 today, we have seen a huge leaps and bound on GPU computing, over, okay, almost 1,000 times better. So to put it in context, Intel Skylake is their 14 nanometer plus 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 plus. Okay, a bit of pun intended here. Okay, if y'all get the joke, all right. Okay, so Intel Skylake processors, all right. So the 14 nanometer architectures, all right, they have quad core or maybe hexa core or octa core processors. Okay, single precision floating operations per second over 4 cores. It can perform 128 giga, which means 128 billion floating operations per second over 4 cores, using 100 watts, okay, with a throughput of 1 gigaflops per watt. Comparatively, an NVIDIA V100 GPU card, or they call it call it an accelerator. They don't call it a GPU card, but they call it a accelerator, because the V family is not meant for GPU, it's mostly for accelerator, can perform 15 teraflops. So 1 teraflop is 1000 gigaflops. Okay, it can perform 15 teraflops at only double the power. This is equivalent to 75 gigaflops per watt. That is the huge improvements in throughput and power, throughput in terms of parallel computation. And because of this, parallel computing has seen an exponential growth in its use cases, in its development over the past 10 to 15 years, in part due to significant advancements in GPUs, which allows us to now use GPUs for general purpose computing. So the reason, okay, so now, yeah, so you can see the reason why GPU computing can also be computationally, can also have bottlenecks, is because of the PCIe, the bus line. Now this is generally your one human's architecture layout. You have your CPU. This is where your CPU is located. Your CPU has a memory controller that's able to access the memory over here. But then how does your CPU communicate with the hard drive, with the network interface card, or with the GPU? It is through what? Okay, using the quick part interface, Intel quick part interface, but it goes through what? It goes through it still goes through the PCIe lane. That's why a PCIe lane can also be a bottleneck. Gen 3 is 16 gigabytes. I think Gen 4 is significantly higher. Just came out recently, Gen 4. AMD Ryzen allows Gen 4. I think Intel's next gen processors will also support Gen 4 PCIe already. So what happens is that to be able to use the GPU, so how it works is, okay, so when you play, let's say when you play a first person shooter game, okay, let's say you play Call of Duty, something like that. Okay, again, I'm talking a bit of gaming. I'm not really a gamer person. I just follow the technology. So if you play a Call of Duty game, the game code is loaded into memory. Okay, and as you play the game, the CPU processes your instructions and things like that, and then it generates the info. It sends the information through the PCI lane to the GPU to do what? To render to screen, to render the graphics to screen. All right. So that is how the GPU works. So a stronger GPU means you can have much more higher FPS. Of course, the CPU also plays an important role here. So the CPU and the GPU both contributes to the high FPS rate of the game. All right. Now, having said that, what they did is that they maintain the same GPU architecture, but they introduce a new library. In this case, in NVIDIA's case, they introduce CUDA. Okay, whereas AMD and other consortiums, they are investing more into OpenCL, not OpenGL. OpenGL is for graphics rendering. OpenCL is specifically for general purpose computing on graphics cards. So by using a library, you can now perform, let's say, matrix operations, vector calculations, all on the GPU. But you need to send the data from the CPU memory to the GPU memory over here. So we will discuss that later on a bit. So at the same time, we have seen advancements in graphics memory. Okay, and from CUDA, NVIDIA CUDA. So CUDA stands for Compute Uniform Device Architecture. It was in 2007 it came up, but actually back in 2006 they already had the early version of CUDA already. And then OpenCL was released in 2008. Okay, so what both CUDA and OpenCL do is that they allow you to copy your data, a single thread data. You copy your data to a GPU, and then the GPU will have hundreds or thousands of threads working simultaneously to compute the task. So this is very good for various arithmetic or geometric computations. Okay, computations over here. That is the whole idea of this method. So from CUDA, what they do is that the CUDA actually, uh, they don't, bear in mind guys and girls, we are not changing the GPU card. The GPU card remains the same. So if you go out today and you go and buy a new GPU card, let's say you go and buy the latest RTX NVIDIA RTX 3080, all right, you can play games, you can do all, you can use the GPU card for all of your gaming or 3D rendering of tasks and things like that. But when you install the CUDA libraries, you can write programs that will also run parallel computing tasks on the GPU cards itself. So you're not getting any hardware changes. It's just that you provide you a new software that transforms your GPU card from graphics processing only to general purpose computing on a graphics processing chip. So that's where, through the CUDA execution abstraction, you can put your threads into blocks, into multi-dimensional array of threads. Now, because why do you do this is because the GPU architecture is designed to work in blocks because it is doing 3D rendering. So we take the same architecture, but we repackage it to be able to to segment your data into blocks of 2D or 3D, which then can be executed in parallel by multiple threads. Okay, that is where we have the threads in block and synchronize, threads in block and access shared memory, and so forth. All right. So this is generally your CPU code. In your CPU code, you write your C code, and then together with the CUDA code, and then you compile using a NVIDIA C compiler. So the NV stands for NVIDIA, C stands NVIDIA CUDA C compiler. Okay, NVIDIA CUDA C compiler. And then the compiler will have both. This is your GCC compiler, and then this is your NVIDIA compiler for the GPU. And then it compiles the code, and then you can run your program on your CPU and GPU now already. And here you can call a function, a CUDA function, by specifying the triple angular brackets over here. This specifies the number of blocks in a grid, and the number of threads in a block. And in this function, you can perform a vector operation over here. Okay, so I will do some examples later on a bit. Okay, I got a private question. How does compiling with CUDA differs from MPI? Now, there's a very big difference here. CUDA is meant to transform your GPU card from graphics processing only to general purpose computing on a graphics processor. So let me explain this to you all. Okay, so let's go back. Let's go back to the slide here. This slide is interesting. Okay, now this is what is in your computer. Okay, so in summary, okay, in your PC, in your PC, okay, all right, you have your CPU and then your GPU over here. All right, so what CUDA does, CUDA allows you to write programs that allows your GPUs to now do parallel computing task, to perform parallel computational task. Okay, now let's say if I have more than one CPU, let's say I have another CPU, also with another PC, let's say I have another PC also with a CPU and a GPU and CUDA inside here, connecting them together. So I got two PCs, and both PCs are connected through a network. okay, through a network over here. So that's a TCP network. Then we can use MPI over here. MPI. So MPI allows you to bridge multiple computers into a cluster by doing message passing at the CPU level. CUDA allows you to bridge a GPU within your PC to allow you to perform parallel computing tasks on your GPU. That's why a few of y'all did in your assignment. In the assignment, some of y'all did what? You chose a topic of what? You all chose a topic of CUDA, CUDA plus MPI. CUDA MPI. Or in fact, that was one of the topics I presented as a suggestion for you all in the FAQ for assignment 1. Okay, where you all use MPI to do message passing between multiple computers. Each computer has a GPU card, which you use CUDA to allow the GPU cards to do parallel computing tasks. All right, so I hope that answers your question for the for this particular relationship. All right, so some simple CUDA examples over here. You can see you have your main function. Your main function takes in one block, threads per block. So you have 3 different types of functions when you create. When you create a kernel functions, a global function means this function is called by the host program. If you put device here, this function is only called inside a global function. It can only be called in the GPU. Okay, that's a host function. So as a whole, when you look at, like, if you look at matrix multiplication, you can see the significant improvements in performance by using GPU cards, because the GPU cards they have many cores that allows you to perform parallel computation for large number of matrices. All right. Now, coming back to the NVIDIA Volta, each NVIDIA Volta card has 64 streaming multiprocessors. Each streaming multiprocessor, so this is one streaming multiprocessor. One streaming multiprocessor has 60, my apologies. Each NVIDIA Volta card has 84 streaming multiprocessors. Each streaming multiprocessor has 64 stream processors or 64 cores. So which means this GPU alone has 84 times 64. It has 5,376 cores. Okay, so the question is, how much does this GPU cost? Okay, how much does this GPU cost? So this GV100, okay, so how much does this GPU cost? Want to give a guess? Anyone want to give a guess? How much does this GPU cost? So if you search up, okay, NVIDIA Tesla V100 price is going for about, okay, it's going for about 10,000 US dollars. Okay, 10,000 US dollars, or roughly about roughly about 40,000 plus Malaysian ringgit. Okay, and I think roughly, yeah. So it's actually it's actually a bit expensive. Okay. Yes, yes. Yep. I hope so. Yes. Okay. All right. Yes, it's my dream to own such a card like this. You know, it's like, yeah, it's like, okay, probably just every night you take this card and then you sleep with this card. Just kidding, the guys. All right. Okay. So this is how powerful the cards are. All right. So those are the things. All right. So generally, this is how the architecture works, the memory architecture and things like that. All right. So that's how it works in that context over there. All right. Okay. So that is the first slide. So give you a very high level to GPU. So now the next slide is just expands further onto how you can. So now you know that you can transform your GPU to do general purpose computing. So this slide gives you an introduction to the CUDA platform. All right. So The CUDA platform, okay, stands for, again, Compute Unified Device Architecture. It provides a library. So CUDA is a software library that allows you to perform general purpose computing on a GPU. All right. So over the years, there have been various amounts of applications and additional libraries developed to support CUDA. So either you can use the CUDA libraries together with C, or you can keep life easy and use the OpenACC directives, just like how you do OpenMP, or you can use programming languages which natively supports CUDA. So let's look at the first one, libraries. So we have NVIDIA libraries. They provide a various amount of libraries from using which are based on top of CUDA. Okay, you have NVIDIA CUBLS. I think the NVIDIA CUBLS, if I'm not mistaken, okay. All right, so the NVIDIA CUBLS is a parallel. Okay, if you go inside here, all right, so it performs various GPU accelerated implementation for linear algebra. So if you're doing matrix multiplication, linear transformations, and if you apply this library, you can get on, and you have a GPU card, you can get substantial performance improvements over in this context over here. So you can actually find a lot of information. If you go to developer.nvidia.com, you can find a ton of information about the NVIDIA CUDA platform. Okay, so now going back to the slides. So 3 steps: you substitute the library calls with equivalent CUDA library calls, and then you manage the locality, and then you rebuild the CUDA library. All right, this is how it works. The second one is using OpenACC. OpenACC is a method where they perform compiler directives to actually transform your code into a parallel code. All right, so OpenACC, if you go to OpenACC, if I go to the website here, I have the website open here. So if you go to OpenACC, I think this is very familiar with you all. You can transform a for loop by putting the Pragma ACC construct. So if you have the ACC library downloaded and installed, so when you compile a code, the compiler will refer to the ACC directives to transform. You will transform this code into a parallel code that runs on a GPU. So it makes life significantly easy for you. No need to worry about this. Like comparing between POSIX threads and OpenMP. In POSIX threads, you have to call a thread function, to create a thread function, you have to call pthread create, pthread join, and so forth. Here in OpenMP, you just put pragma OMP parallel for, and it's all done for you already. So the same concept actually applies here. Okay. The third one is by using the programming languages. So you can use CUDA C, which we'll do later on a bit. All right, so this is how you can actually do CUDA. You can actually do parallel computing on using CUDA platform. Now, I'm not saying that I'm aligning myself, or these nodes are aligned to NVIDIA. I mean, we are using NVIDIA resources, so that's why in this case NVIDIA is promoting more of their hardware architectures and their libraries. But you can also use OpenCL also. Okay, it's more applicable to across general GPUs, whether NVIDIA, AMD. It's just that NVIDIA's CUDA is way more optimized to run on the NVIDIA cards that gives way better performance, and that's how it works. Okay, and if you notice, today's deep learning. Okay, today's deep learning. Are you all familiar with deep learning? Are you all familiar with deep learning, guys and girls? Are you all familiar with deep learning? So, right? Are you all familiar with that? So. Okay. All right. What is deep learning? I should put another question over here. 1 second. Okay. New poll. Maybe I should put a new question over here. So, what is deep learning? Who can tell me? I've already started a new poll. What is deep learning? Can anyone just type your answers inside here? Are you all familiar with deep learning? What do you think is deep learning? One person has answered. Okay. Yes, deep learning is in a way neural networks. Okay. So if you Google up deep learning, it's like the buzzword today. Yeah? If you probably be hearing as a computer scientist, yeah, sincerely speaking, it's good to know deep learning in today's industry where everyone is literally looking at how they can use deep learning to automate their processes, whether in the manufacturing industry, banking, government, healthcare, you name it. Okay, e-commerce and so forth, automation, autonomous driving and things like that. So deep learning is a subset of artificial intelligence that mimics the workings of a human brain, okay, for processing data used for detecting objects, classifications, and making decisions. All right. And here's the thing about deep learning. If you look at the underlying architecture of deep learning, I'm not going to go into deep learning. There's a unit dedicated for this topic. All right. If you look at the underlying architecture of deep learning, it's actually running a lot of linear algebra operation, linear transformation operation, huge amounts of matrix operation, okay, matrix and vector operations. And that's why if you are going to train a deep learning model, let's say if those of you all who are tinkering with deep learning, if probably you have used PyTorch or you have used TensorFlow and things like that, exactly Kin Wang has mentioned, okay, FIT3141 is a unit, okay, that does deep learning. If you go into deep learning, you will notice that you need a good GPU card. Okay, you need a good GPU card, especially those of you all doing object detection or those of you all working in generative adversarial networks. Okay, you realize that you need a very good GPU card. Why? Because deep learning underneath it's performing huge, enormous amounts of matrix operations, which a CPU just cannot handle. That's why you need very powerful GPU cards. That's why having an NVIDIA graphics card like the GeForce 1390 or the Quadro family or the Tesla families allows you to perform accelerated deep learning research. Okay, and those are, and if you look at NVIDIA, I mean, if you look at TensorFlow, PyTorch, beneath the libraries, beneath the frameworks, they're all using CUDA for GPU acceleration. Okay, so I got 4 people answered here. Thank you. Okay, so let's see the answers. Okay, deep neural network, high performance machine learning, something to do with AI, self-learning technology. All right, and same thing. Yes, I got a private message also. How about Bitcoin mining? Exactly, Bitcoin. If you go to Bitcoin, if you just type Bitcoin and GPUs, you will find, okay, GPU usage in cryptocurrency mining. It is very important. GPUs play a huge role, and underlying all of the cryptocurrency mining algorithms, they're using CUDA. So what you're learning here, CUDA, what you're being exposed here is the baseline. Once you understand CUDA, you can write so many applications on top of using CUDA to access the GPUs to perform parallel tasks. Yes, okay. That's why the GPU for parallel computing is actually an important knowledge to have. It's not you're not being examined for this, but it's an important knowledge. I mean, if you were to go into GPU computing alone, if you want to really master GPU, if you want to really master GPGPU computing, you want to take 1 semester. All right, so that is it. So that's why we I mean, at least we hope that when you go back, you will actually make the initiative to actually try to do some self-study. I mean, this is purely based on your initiative. Yes, okay. So I got a private question. I think Beijing is a very good question. All right, so I would like to share this question with everyone here. Okay, I'll just open a new slide over here. So let's remove this. So the question is this: do we need to set up or activate the GPU in our device to use it? Or whenever you code in CUDA, the code will automatically run on GPU. Now, the first things first, if you are going to do a GPU, okay, the first thing you need to do first, okay, maybe I should make this smaller. Okay, okay, and then make it here. All right. So, Peijin, thank you for your question. The first thing you need is you need a GPU card. You need a GPU card, a compliant GPU card. GPU card compliant with, let's say, compliant with CUDA or OpenCL. Okay, so example, if you just say the current ones, like NVIDIA, okay, yes, for CUDA, for CUDA only NVIDIA cards. Okay, for CUDA only NVIDIA cards. Let's say GeForce RTX 3090. Oh, what a wonderful card! This one, amazing card, lah. Okay, probably in this summer, kid need to buy this card. Just kidding. Okay, the last lecture already. Okay, second thing, then you need to install CUDA on your computer. Whether you're using CUDA works both on Windows and Windows. I think they have also CUDA for Mac, if I'm not mistaken. Windows, Mac, and Linux. Okay, but I can't be sure for Mac. I don't use Mac, so I'm sorry about that. Okay, then once you install CUDA, then you can write and compile parallel applications which will run on a GPU. That is how you do it. Okay, Peijin? All right, that's how you do it. Now, having said that, all right, so yes, Darren, Mac, you need an external, you need an external GPU. Yes, I should put here, you need a discrete GPU. Not integrated, you can't use integrated GPU. You need a discrete GPU. I mean, integrated GPU, you can use OpenCL, but we're using CUDA, you need a discrete GPU. Okay, this is where I say GeForce RTX 3090 or 2080 Ti and things like that. Now, nowadays, for deep learning, let's say for deep learning, when you install PyTorch and everything, they will ask you, they already ask you to install CUDA first. So you just write the code, and then behind the code, they will do all of the CUDA function calls. Okay, and things like that. So these are the steps you need to do. All right. Now, the thing is, if you're wondering, well, this is so interesting, why didn't we have a lab this semester and things like that? That's because you need a GPU card. And not all of you all have a discrete GPU card. Most of you all may be using laptops with integrated graphics cards, which you can't use CUDA. You probably can use only OpenCL. So, but okay, yes, okay. Now everyone say, what about Monarch? What about Monarch? Yes, exactly. Okay. Now, if you go to Monarch, documentation for Monarch, initially we were given the old ones, the old Monarch course. This one, I think the HS ones. Initially, the FIT3143, partition, we were given this one. These servers don't have a GPU card. Later on, remember I made an announcement, please change the partition name from 3143 to ECE4179. Those partitions have a NVIDIA Tesla P100 card. Okay, so yes, in those cards, but we were given at the last minute because I think they fell for us or what, something like that. But if you look, they said please use the ECE4179 partition name. So if you go to Monash ECE4179, what is Monash ECE4179? It's a neural network. It's a neural network unit which is offered at engineering. Okay, just like FIT3141. All right. So that's why at the end, due to time constraints, we thought, okay, never mind. Now, having said that, you can use Google Colab. I'm going to give you a demo later on shortly. You can use Google Colab to actually, run CUDA on GPUs for free, but limited. There's a limitation over here. All right. So that's where part 3's lecture notes come into play. C. Okay. So in C, we given you a slide. This is taken from NVIDIA. What is CUDA? How do you do CUDA? What is the prerequisites? You need experience C. You don't need GPU experience. You don't, okay, this is a bit wrong. I mean, it's good to have some parallel programming experience. You all have it now already. Okay. So the concepts of these slides will teach you all how to write your first parallel computing code on a GPU. So when you say host, so a terminology that you need to understand here is the host CPU and the device GPU. All right. So host means your CPU, your host memory, and then your device GPU is your device card over here. So what you do is that you can then have your C code, and then you can have your parallel code running on the GPU by calling the GPU specific functions. Okay. So the host code will run on the CPU, and then the parallel code will run on the GPU here. All right. So the simple process is this. This is your CPU. This is your GPU. All right. You copy your memory. Let's say you want to do a matrix or vector operation. You copy the content of the vector from CPU memory to GPU memory. You do that first. Then after that, you load the GPU program and you execute it. Okay. And then you copy the results of from the GPU memory back to the CPU memory. So one example. So give me 15 minutes to go through this with you all. Just after that, I'll give you a break. Okay, I'll give you a break. Okay. So one example is here. So let's say I have a simple main function. I've installed CUDA. I compile CUDA. I do NVCC compiler. So all the while last time you were using GCC, then you use MPICC. Now you use NVCC. Okay, NVCC. All right. You compile a code. Now, when you compile a code, nothing happens actually here because this code doesn't call any GPU functions. Now, when you want to call a GPU function, you have to call a function name, and then you have to specify this magic word, this magic key here, this one. Okay, this magic key, this one here. Okay, this is where you specify the number of blocks within a grid and the number of threads within a block. Okay, so how do you create a GPU function or a function that runs on a GPU? So CUDA keyword global indicates that this particular function. So this is what we call the calling convention. By specifying the calling convention here, the compiler knows that this function will be executed on the device, but this function is called from the host. So the NVCC compiler will separate the source code into the host and device components. Okay, you have your device functions, you have your host functions over here. All right. So when you call my kernel 11, the triple angle brackets mark a call from the host code to the device code, also called a kernel launch. That is all you require to execute a function on GPU. Yeah, it sounds simple, but actually there's more to it. All right. So now when you compile this code, the compiler, the NVCC compiler will see, oh, I'm calling this function. This function is called by the host, but this function will be executed inside the GPU. Okay. So this is where you can perform vector operations. So now let's say we got two vectors. We have done this before on many occasions already. Okay, we have done this before on many occasions. Let's say you got two vectors. All right, I want to add both vectors and store the answers into a third vector. And I want to do this in parallel. Okay, I want to do this in parallel. So imagine if you were to do this, in C, what do you have to do? You have to do what? For I equals to 0, I less than n is the vector size, I plus plus, then what do you do here? You do the vector, let's say vector C at location I is equals to vector A at location I plus vector B at location I. Now you've learned, let's say your n is 10 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. Very huge vector. Now, of course, if let's say if you're doing let's say POSIX threads parallelism, POSIX threads. Okay, and let's say we create 8 threads. 8 threads. So which means each threads will take what? 1.25 billion elements of the vector. Okay, 1.25 billion elements. So which means that here you will replace the 0 and the n with what? Start point and end point. Where you calculate, each thread will calculate their own start point and end point based on the thread ID. We have done this before already. Now, how can you do the same on a GPU? That's where things get very interesting. So when I call the add function, I just dereference to the memory and I add it. This is a very simple example. Okay, this is a very simple example. Now, the idea is actually this. Now, you see, you first need to transfer the vector from CPU memory or host memory, this is host, to device. You need to transfer the vector into the device memory. That's why you need to call CUDA malloc. CUDA malloc is like you're creating memory which can be transferred from the host to the GPU memory. All right, so you can see over here, I will create the CUDA malloc. So instead of calling malloc, so you don't call malloc anymore. You call CUDA malloc that creates the memory which will be used by both the host and the GPU. Okay, and then you call CUDA memcopy. CUDA memcopy to copy the host variable into the GPU memory. And then you pass in the GPU, the GPU address memory into the CUDA function, and then it will perform the task for you. And then once you're done, you copy back the GPU answer memory, the answers in the GPU host, the device memory into the host memory. And then you can store the answers into your file. So I'm going a bit fast over here because the slides are very good. They provide you a very clear understanding. So now, now we go into parallel part. Let's say I want to perform a vector operation. So let's say I want to create n number of blocks. Each block got one thread. Okay. So the idea is when I call the add function, I want to get the C at block ID X. So these are all internal variables of CUDA. They already predefined variables of CUDA, so you don't modify them. Okay, so the block ID X.X tells you what is the ID of the block for that particular thread that is executing the operation. All right. So as you can see over here, when you call this function on a GPU, the GPU will create multiple blocks that will run concurrently in parallel. Okay, they will run simultaneously. Each block will take a different element of the array and perform the addition simultaneously in parallel. It will do it in parallel for you. And then when you return back, so the main function does something like this. So you create 3 pointers. I do CUDA malloc 3 times over here. I create my malloc, and then after that I transfer my host memory. I transfer my host memory into the device memory, and then I call the host. The host calls the device function. The device function then performs the operation on the GPU. So this will be carried out on the GPU. Will be executed not on the CPU, but on the GPU. That is the power of it. All right, and then you free it up. All right, now the second option is you can now use threads. Rather than using block IDX, I can use thread IDX, because one block. So in CUDA actually it's based on a 3D grid. One grid can contain multiple blocks, and one block can contain multiple threads. All right, so earlier on in the earlier example we only use one block, but now we want to use multiple threads within a block. So over here now you can see I've swapped the roles. Here I only specify one block and threads within this block, and the rest of it is still the same. The function is still the same, but we call thread IDX now. Now, the ideal goal is to do indexing, where we combine the blocks and the threads. So how we do this is we actually now, each block contains multiple threads. And we can do an indexing by performing a simple arithmetic operation by taking the thread idx.x plus the block idx times m. So guys, let me ask you a question. Let me see whether you're paying attention or not. Let me ask you a question. So let's say for this one here, number 2. What is the index, what is the overall array index for this particular value 2 over here? Block IDX is 1, thread IDX is 2. What is the answer? And let's say your M is 8. Your M is 8 over here. What is the answer? 10. So what do? You substitute 2 over here plus block IDX is 1 times 8. What's the answer? You don't do 2 plus 1, 3 times 8, 24. It's wrong. If you remember your operation precedence, multiplication always occurs first. So actually you do 1 times 8 first, then only plus 2. So the answer is correct by Darren. The answer is 10. The index is 10. Okay, that's how we do it just now here. All right. Okay, so we can use the block dimension x. So these are all predefined variables by the CUDA compiler. So now you change them. So inside here, we can get the index, and then we can call the index of each array and perform the operation. So you can see, guys and girls, do you see any for loop here? No. You try not to call for loops in a CUDA thread function. So in a CUDA function, okay, in a CUDA function, try as much as possible not to call, okay, no loops. No loops. You specify the index inside here. Okay, because the idea of the CUDA function is to minimize non-arithmetic instructions. All right, that is the idea of CUDA. So inside here, when I call the add function, I can put a comma here. The n is the size of the vector. I can define how many threads per block. Let's say I want to specify one thread of 512 blocks. So this one is also based on the, this is also based on the CUDA specifications. Typically it's 512. Typically it's 512 threads per block. Okay, oh sorry, so no, 512 threads, sorry. Yeah, correct. My apologies. 512 threads per block. My apologies. I got slightly a bit misled there. So your n, so this in this case your n must be very large, larger than 512. You divide by the threads per block, and then how many threads inside here. So in this case, let's say your n, if let's say your n is 2048, 2048 divided by 512, so which means I'm having 4 blocks over here. And then one block contains 512 threads. So which means it will split this vector. So your vector has a size of 2048 elements. Each the elements will be split different blocks, and each block will run, and the blocks will run in parallel on the GPU. All right, that is how it works inside there. Okay, so that is the idea. So now the rest of them you can, as far as memory is concerned, that one I'll let you all go through it on your own. Now, how do you, I mean, now you get the idea. How do I get CUDA working? Okay, so dang, you can go to Google Colab. Go to Google Colab. It's free, yeah. You just need a Gmail account. You just need a Gmail account. You only need a you can use your Monash account. You can use your Monash account. Okay, sorry. Okay, it's free. It's a free version now, all right, but it's limited all right. You have access. You have free access to NVIDIA Tesla cards, K80 cards hosted. Okay, so Google Colab. If you look at Google Colab, if you search for Google Colab GPUs, what GPUs are they using? Okay, which GPU is Google Colab? So normally they're using Tesla K80s. They provide you Tesla K80s. All right, so Google Colab is a free one. Okay, you don't need NVIDIA cards. No. So let's say I don't have an NVIDIA card. I don't have my laptop. Let's say I'm using a tablet. And I want to do, I'm very interested on GPU programming. Today's lecture has been very interesting. All right. So Google provides you cloud hosted. Google Colab is a cloud hosted services. Okay. Google Colab is a cloud hosted services. Google Colab architecture, something like that. If you search it up, maybe you can find some links inside IS. Okay. So Google Colab is a cloud hosted application. So it's supported by Google. They've probably got hundreds of servers or more than that. Okay, which they provide you access through Jupyter. I mean, using a Python notebook over here. All right. So what I've done is I've used Google Colab to set up to run my CUDA, to install CUDA. All right. And then after that, after I've installed CUDA, I can check my NVCC version. So you can, I mean, I'm sure all of you are familiar with Jupyter Notebook. So we are using the same Python notebook over here. So now I'm using version 10, and then I'm installing the NVCC plugin for Python notebook. Okay, and then I'm loading the Python notebook. Okay, then inside here, you see, this is the code. So this is the code which I've created. Maybe I can zoom in a bit for you all. Okay, so I specify code here, then I put triple column. So I specified a code here. So this is a random generator function. So this is the CUDA function over here. Okay, this is a CUDA function. You call add. You can see we get the index, as I mentioned, the slice is now, and then we call the index array inside here. In the main function, I declare pointers, CUDA malloc to allocate the device memory, then the CPU malloc to allocate the host memory. You copy the host memory to device memory. You call the CUDA function, your function over here, add function. You specify how many blocks per grid, how many threads per grid, and then you specify the device memory addresses inside here. Once that is done, you copy back the device memory answer into your host memory, and then you can print out the results. And then you free the memory over here. Once you've done this, you write this to a file. Oops, I forgot. Sorry, I forgot to run this. Okay, now I can run this. Yeah, done. And then I call a CUDA compiler. So the NVCC. So you don't call GCC, you don't call MPICC. You call NVCC, and you specify the code.cu. So you don't longer call code.c. It's called code.cu. It's a CUDA code, but running on C. Okay, you run the code. No errors, and then you can run the application, the output application. But this one here, nothing happens because I'm not printing anything. But you can see, you can do the NVIDIA profile by calling the NVIDIA profile of the output application. It will show how long it took to run the GPU activities. Okay, the API calls, the CUDA malloc, CUDA memcopy, CUDA launch kernel, and the functions, how long it took to run. Okay, so this is a good exposure for you all to run Google Colab. Now, if you're asking, hey, can I have some tutorials or not? Yes, I will pass the tutorials to you all. How to run, there's an article in Medium, how to run CUDA C on Google Colab. Okay, this is a very good article. I will post this article in the Moodle page for you all to refer to. It is not necessary for you all to do this. You can also type the code directly inside here, but I found it that it's actually better this way because you don't get affected by the indentation rules and things like that. Okay. All right. So that is a hands-on exposure to CUDA for you all. Okay, now guys and girls, any questions or not? Any questions or not? Do you find it interesting or not? Do you think it's interesting or not? Okay, so all right. So so I got a follow-up question for Iwan. What industries CUDA programming is used? CUDA is the backbone. Guys, CUDA is the backbone in deep learning. CUDA is the backbone in deep learning. If you just type TensorFlow, Google, or just type Google TensorFlow on CUDA. Okay, so they actually implement the CUDA DNN version underneath. So deep learning uses CUDA. So CUDA provides you the framework to access GPUs for general purpose parallel computing. All right, so I hope this lecture would have given you an eye-opener to what parallel computing you can do on GPUs. All right, so at the end of this unit, you're now familiar with doing parallel computing on CPUs. You're now familiar on doing parallel computing across multiple CPUs using MPI. Before that, POSIX threads. And then now you have some exposure on how to do parallel computing on a GPU. All right, and then you can expand your horizon to do how to look into CUDA. There's a library called CUDA MPI. CUDA MPI, developer MPI. Okay, a very brief introduction to MPI. CUDA aware MPI. So you can run an MPI program on a cluster of computers. Each computer has its own GPU. So they give you an example on how to do this. So developer.nvidia.com provides a lot of information about all sorts of resources for applying parallel computing on a GPU. All right, so it's a very good website here. Okay, so that's it for today's lecture. I mean, for these 3 parts here. Any questions or not? I'll give you a 5 minutes break. Then after that, we come back and then we do the last revision, the revision of the lecture notes. Is that okay?
Sir?
Yes.
Can I discuss about the assignment? I mean, I have some problem with the make file.
Uh, yeah, let me pause the recording first. The assignment was due already. Okay, never mind. Anyway, I paused the recording first. All right, so I've continued recording the session, and I'm going to do the last part of the lecture, which is the revision. Okay. Okay. So okay, can you all see the screen? Can you all see the screen? Can, huh? All right, all right. Okay, so let me reset. And where's the last one? Okay, so now we go back to our revision. So, okay, so now we have come to the last part of the lecture. So I'm just going to quickly go through with you all. I mean, in the past, I used to spend more time on the revision because we didn't like record the lecture videos. You're all on campus, so many of you would have forgotten what you have learned in week 1, week 2, week 3, week 4. The good news is now we have lecture recordings all in the YouTube video, and so you can refer to them. Okay, so I'll just quickly go through with you all what we have learned. So this should be very fast. So in week 1, we were introduced to parallel computing. Okay, generally the idea of parallel computing is to break down a serial problem into a data parallelism problem. Okay, then second, guys. Okay, just want to make sure. Yeah. Okay. All right. Then after that, then so we compared shared memory parallelism. So in shared memory parallelism, you have multiple processors within a single computer that have access to a common memory. So this is the basis of your multi-core architecture. And then I also introduced you to distributed parallelism, where through a network you can interconnect multiple computers to form a cluster. So generally, we have discussed the difference between parallel computing and distributed computing. Okay, so this is what we discussed in the first week of lecture, and then we went through Amdahl's law. So how you can compute theoretical speed up. So at least now, before you all do parallel computing, you all can actually do a theoretical speed up of a serial code which can be parallelized to get the motivation, whether or not is it worth parallelizing or not. Okay, most of the cases, yes, but this gives you a more objective analysis. Then in week 2, I introduced you. So week 2 was a hands-on lecture where I introduced you all to shared memory parallelism using POSIX threads and OpenMP. Okay, so that is the week 2's one. All right, so that is what we did. Okay, just a second. Okay, so that is in week 2. So now, so in week 2, we learn to how to use POSIX threads and OpenMP to actually parallelize your code. Okay, so we did a lot of hands-on explanation. So POSIX threads, so POSIX threads, as you know, you create the thread functions, and then after that, you wait for the thread functions to complete. All right, then inside here, we learn. So this is a process. This is your process. You've got the instruction pointer, your code segment, your stack, a heap region. In threads, each thread will have their own stack memory. Okay, the stack region, and then the code segments, and then a heap region. So the threads will share the heap region of the memory code. All right. Okay. Just a second. William, I think can you help me mute the microphone? Okay. So, okay. And also, yep. Brian also. Okay. Thank you. Okay. Thank you very much. So in week 3, we went into inter-process communication and remote procedure call. So here I've highlighted the importance on IPC. What is the purpose of IPC? what are the differences between synchronous and asynchronous communication. Okay, so generally this is a theoretical discussion. All right, and from here we went into the different types of failures in IPC. How do you implement idempotency? Okay, and then the 3 types of communication groups. So the bold points are the important ones for you all to take note of. Okay, where we learn about remote procedure calls and 3 different types of implementing concurrent access. That is where in week 4 we went into our again hands-on lecture. So week 2 and week 4 very much hands-on lecture. Week 2 was in POSIX stress, and week 4 I introduced you all to MPI. So you learn all of the MPI functions. Okay, how to do MPI communication. So by now you all know MPI. MPI is to provide a means for you all to do message passing. Okay, message passing between processes. And then in week 5, I introduce you all to synchronization, mutex, and deadlocks, where we learn about clock synchronization. Okay, so the bold ones are important. Christian's method, Berkeley's algorithm, averaging algorithm, and then we learn about Lamport and Vector's clock. Okay, then we covered about mutual exclusion, where we covered centralized, distributed, and also group mutual exclusion. How we can handle deadlock detection. In week 6, we went into election algorithms. So from week 5, week 6, week 7 was all very much theoretical base. So election algorithm, okay, the bold ones are important. We cover Boolean algorithm, ring algorithms, and then in distributed transactions, we discuss about different types of distributed transactions, how we can perform multiple transactions, how you can perform transactions across distributed servers, and how can we maintain the consistency of the transactions. And then in week 7, we discuss about failures and false and distributed consensus. So we discuss about crash failure, omission failure, transient failure, bicentennial failure, and things like different types of failures and how we can do fault tolerant systems. Now in week 8, we went into theoretical, but we have a lot more better understanding on the architecture. So this is important, where we discuss about instruction level parallelism, how we can transform a scalar, how we can introduce parallelism into scalar processes through pipelining. Okay, we discussed about pipelining. Okay, and then we did how we can apply pipelining for the fetch, decode, execute, and write back operations. So we discussed this. Okay, if you have forgotten, please refer to week 8's lecture video. Everything is covered very in depth inside that. Okay, and from here, by applying pipelining, we can get the pump prime version, where all at this point we have achieved parallelism, where for different instructions you are going through different phases. I mean, for each instruction is going through different phases of the instruction execution. And then from there, we learn how we can expand instruction level parallelism by having multiple execution units through VLIW or superscalar. This is the foundation of your SIMD architecture. Okay. Then in week 9, we went into vector architectures. So in vector architectures, we talk about vector processes, and one very important part is interleaving, where we learn how to do interleaving in vector architectures. So how multiple reads happen. So each read consists 2 cycles, computing the address, reading the address. Okay, and that's why we put the memory in this particular architecture. So this is something I would implore you all, please go and refer to week 9's video to get a better understanding on how we do interleaving. All right. And then in week 10, in one slide I summarize, we discuss SSE, SIMD, from MMX, okay, MMX instructions to SSE, SSE version 2, SSE version 3, SSE version 4, AVX. So in the exam, it is important for you to understand the difference between the different versions of SSE, what are the features, what are the new additions inside there. All right. And then finally, in week 11, we discuss about distributed MIMD. Okay, what is MIMD architecture? What is the difference between shared memory MIMD and distributed memory MIMD? Okay, what are the challenges? What are the constraints required to actually implement distributed MIMD? So that's the lecture. So I got a private question. Do we have to remember SSC? Yeah, you have to know. Yes, you have to remember the features. We're not going to ask you to memorize the instructions. No. But you need to understand what are the different features between different SSCs. What are the evolution there? So that should be quite easy to remember. Okay. So we did our tutorials. I think if we refer back to our tutorials, that will give you a good idea. All right. Okay. And that's it. Okay, so you can look at it. I mean, initially you may think that there's a lot to learn and remember, but in actuality, it's actually pretty okay. All right. Then in the labs, you had an exposure to Linux, then C programming, and then we introduced you all to labs on POSIX threads, labs on OpenMP, and then we did labs on MPI, and then we went further into different types of MPI, communication, send, receive, and then we introduced you all to MPI virtual topology, okay, and then from there MPI complete, and then from the labs you did the assignments, okay. All right, so that is the thing. All right, so now your final exam is on 1st of December 2020, Tuesday morning session, which is 10 o'clock morning Australian Eastern Daylight Saving Time, which is 7 o'clock morning Malaysia time. I know, I'm sorry again. I tried discussing on moving the time long later, but I was not successful. So guys and girls, please, especially those of you on the Malaysian campus, just for one day, please make sure you get up very early in the morning to do the exam. Okay, let me repeat. The exam is on 1st December. Those of you on the Malaysian campus, your exam is on 1st December, 7 a.m. So if those of you who are on the Malaysian campus, if you have returned back to your home country in Indonesia, you have to adjust your time accordingly, please. Or Bangladesh or Middle East or Sri Lanka, India, or any other countries, please, yeah, exam. I hope so. Yes, I'm sorry, Ivan. All right, very sorry about it. Okay, just once, just for this once. Okay, please, yeah, try a level best. Okay, try it. Just make sure you have to set alarm time, inform. If you're staying with your family, make sure they are aware about this. You need someone to give you a wake up call. Get someone to help you do the wake up call, because guys, the exam is very doable. Trust me. So don't waste the opportunity by not doing the exam and then applying for supplementary. All right, the exam is designed such that it actually helps students to pass. Okay. So the exam details, the closed book supervised exam. The actual exam link is here. Or this is for the Malaysian one. If you click the my, but maybe I should have, probably I should have, yeah. Yeah, this is the one, eassessment.monash.edu. I should probably edit the link, and also, yeah, this is the correct one. Okay, eassessment.monash.edu. All right. There's no drawing required during the exam. Okay, you not required make any drawings. The topics will cover everything from week 1 to week 11, lecture, labs, tutorials, and assignment 2. Okay, there are 3 parts in the question exam. Part A, 4 short essay questions. Each question carries 10 marks. So you can give your answers in point form format. Okay, you can give your answers in point form formats. It's a closed book exam. So you're not supposed to look at any notes. They will have a software that monitors your face movement and eye movement. So if you keep looking down, something like that, the invigilator might contact you. So try a level best not to have any notes with you all. But I think you all should be in good hands. The questions are not, if you refer to tutorial questions, you should have no problem doing the exams. It should be okay. No draft papers allowed. It's a closed book exam. No, I'm sorry, no. I'm sorry, no draft papers allowed, as far as I know. Okay, so you don't need it. You don't need it. You can type everything inside that. The questions are quite straightforward. So don't worry, Paging. All right. Okay. Part B is programming. You can't write anything on the blank paper. Not supposed to. You're not required to. Not supposed to. Not not supposed to. Okay. And you're not required to. Not required to. Calculator, yeah, I've removed the calculator restriction, so you can bring any calculator in the exam. Wait, did I remove the calculator restriction? I think so. I did. Yeah, I'll double check on this. Okay, but you don't actually need to do any complex calculations also. So I hardly believe you'll be using calculator. All right. So there are two programming questions. Yeah. Yes, there's no restrictions as far as I know, as far as I recall. As far as I recall, no calculator restrictions. As far as I recall. Okay. Yeah. All right. Yeah, I believe so. Can. Yeah. Yeah. Possible. Yeah. Can. I don't see any problem. Okay. So, two programming questions in part B, each 20 marks. One question on POSIX, one question on MPI. All right. And you'll be given the starter code, so you just need to complete the code. All right. So practice your labs. I think they'll give you a good idea. And then part C is one case study. So case study will give you a problem. So the problem can be in a way similar to your assignment question, assignment 2. And then we will ask you to study the problem, explain your understanding on the architecture. Why do you think this method needs to be implemented? Why this method works this way? And then we will give you some code to complete. Okay, so that's the part C question. Now, what happens if you get the MPI syntax wrong? If the MPI syntax, so we will give you a list of MPI functions for the programming questions. So for the programming questions, we will give you a list of MPI functions which you can use. We just give you the function prototype, so that will so you don't need to remember much. No, for part B, we hope to see coding. So for part B, try to avoid writing pseudocode. You can write coding, but not necessarily have to be perfect. You can, if you miss a semicolon here and there, it's fine. It's fine. Okay. All right. We will provide for part B. We will provide the MPI or POSIX threads function prototypes. So there's no need for you to remember. Okay. So that is the part, the exam. So it is actually a fairly straightforward exam, if you ask me. It's not a very difficult exam. I think I hope to see 100% passing rate. Of course, HDs might be a bit, there'll be one or two questions there that makes it a bit more trickier to get HD. But I think largely the rest of the questions will be very straightforward. Okay. So that is the exam details. In week 13, we will provide a mock exam link. So the mock exam link is this one. Again, why do I make this mistake again? Shouldn't put. Yeah. 1 second. Sorry about that. Yeah, this is correct. Okay. All right. So just type student eassessment.monash.edu. All right. And then the mock exams will be released on Monday SWOT week. That's target. So I will provide consultations for you all during SWOT week, Asian week. So please do the lab practice. Please do the assignments. Please go through the assignment code again. Please review the online lecture recordings and tutorial recordings. Tutorial recordings, I will share to you all privately, those who want it. Yeah. So maybe, so Darren, you have a good question. So if you allow physical calculators and you put it in a table, how is that different than having draft papers on the table? So as far as I know, before the exam starts, Darren, before the exam starts, the invigilator will ask you to declare whatever you have on your table. So that's where you can declare, Darren, you have a calculator and things like that. All right. So once the exam starts, whatever you declare should only be on the table. You shouldn't suddenly introduce something into a table. Then that can be constituted as violating the exam rules. Is that clear, Darren? They might ask you to do that. So Darren asked a question: do we need to move our laptops before the exam starts? You may be asked to move the laptops, or you may be asked to move the webcam to show that there's no one around you in the exam. Yes. So I know this is new to you all compared to last semester. Last semester was non-invigilated. So this time is invigilated. So some of you may have some privacy concerns, but please give this a try. Okay. You can tell the invigilator that you don't have a closed room. I mean, preferably you should. So the question I got is, can the exam be conducted in a closed room? Preferably yes, but if you don't have a closed room for some reason, then you just inform the invigilator. I have to do it. I have to do it in my. I have to do it in my hall or something like that. Now,
Okay. Assume that if the exam, I mean, I assume that if the campus is already open by the time exam is there, right? If I do the exam in the campus, like what should I do though? I
just come to
mean,
campus. They say you want to do the exam on the campus.
I
I
mean,
mean,
like,
like,
is there any room where I can do the exam or something?
not really. I mean, the Hive is the only place, I guess.
I see.
Yeah, the Hive, or yeah, the university is not. I mean, prior to the lockdown again, they really opened up a library, so you can use the the computer cubicles in the library to do the exams. It's possible. Yeah, if you want to. Now, as far as for network disconnection, the same rule applies last semester. The exam will still run. So if you get a network disconnection, you have to immediately, once you get reconnected, you have to immediately inform e-solutions. And if you think that the disconnection was so bad that it affected the exam, then you need to write to them to ask for supplementary exam. So the same rule applies in semester 1. Yes, just like what you did, Darren, last semester. You should please check, please refer to this site. They already provide all the information inside here. No, they'll give you a number. So there's no chat box. They'll give you a number. You contact a number. The number connects you to the Monash Malaysia ITS number. All right, and then they will take note of it. Yes, that's the one. Yes, the one William shared. Exactly. Okay, it's a bit different from Australia. You contact by phone. That is true. Yes. Yes. Now, let me ask you a question. Last semester, did anyone have any problems networking during the exam? No. So it depends. So you can have your phones. You can tell the invigilator that your phone is there as a backup in case your home network goes down. You have your phone as a hotspot. So you can do that, guys and girls. So try to be a bit more, apply a bit more backup. Yes, at home you have your home internet, your network, your unified network, or you're using time network and things like that. You have it there, but you have to prepare. I mean, I'm sorry. I mean, I wish there's a better way. Okay, I wish there's a better way, but for the exam, for the sake of the exam, you need to have a backup. Yes. So that backup includes having multiple, you can't have multiple monitors. You can't have multiple monitors. I think it was mentioned inside, one second. Yeah, inside here. if you go to the device specifications, you won't be able to use dual monitors. Okay, but you can have a backup computer standby, whether it's a tablet or something else. Okay, you can have a backup computer standby. You can inform the invigilator. The invigilators are not going to be they're not going to be like, oh, you are doing something wrong, fail the exam. No. They are quite sensible. Okay, as long as you follow the basic procedures, you should be okay. All right. Yes, Darren definitely can. Of course, you can do that. So Darren ask, can the backup computer be turned on and be prepared before the exam starts? Yes, please do so. You can do that. You can just keep it aside and say, this is my backup computer. In case anything goes wrong, I will immediately switch to it. All right. The good thing is our exam is on 1st December. So I'm sure by then most of you all would have done other papers already. So at least you all already gone through it, so you know what's going on and things like that. So when it comes to our paper, it should be much more smooth sailing compared to those of you all doing the first papers in the first week and things like that. Okay. So that is the yeah. Yeah, so I know I sound a bit cheeky by saying that, but in a way, well, the one advantage of having parallel computing on week 3 is that we have this slight advantage over here. Okay, so on a final note, okay, thank you very much. Okay, thank you very much. Again, before that, please complete CERTU again. Again, guys and girls, please do me a favor. Please complete CERTU for us. Okay, your overall unit satisfaction score is very important for us. Okay, it means a lot to me. It means a lot to the teaching team to complete the CERTU. So at the end, thank you very much. You've all been wonderful students. I know it's been a very tough semester. It's been a tough year. It's been a really, very tough and miserable year. We are living in unprecedented times. But at the same time, you guys and girls have been very resilient. So thank you very much. Thank you very much. Thank you, Peijin. Thank you for this. Thank you.
And sir, I still got another question, but one last question about the make file though.
Maybe the one after after I start recording, I'll come back to you again. All right.
Okay.
Okay. So thank you very much. Thank you for enrolling this unit, and I hope you have learned well. I hope now parallel computing will be something very interesting for you all. All right. I hope you all. I trust all of you all do well in the exam. I'm going to have a tough time writing an exam report. Give a justification why the students did very well. Okay. So I hope yeah. Okay, so I think I have the data to support my argument, so don't worry about it. Okay, so you all did very well. I think if you all do well, you all earn the results. So please do the exams, and if you have any, once assignment 2 is out, if you have any, please make sure you all do well. The interviews will be conducted by Mingje and Jesse, so they understand you all, so no worries. So just talk to them nicely, and I'm sure you will have a good interview with them also. All right. Okay, so yeah, now, yes, for next year, before you all leave, for next year, I will be doing this unit 3182. Okay, big data. Yep. So I will be doing this unit 3182. So big data extends parallel computing to the next level. Okay, you will be learning how to use big data architecture. So this is a data science unit.
Is it like something like Spark and Hadoop?
Exactly, yes. I will teach you how to use Spark, how to use Kafka to create a big data stream architecture. So we'll be doing parallel computing on big data. So this is a very interesting unit. So if you've done parallel computing, now you're familiar with MPI, message passing interface. Big data is about map reduce architecture. It's a whole different parallel computing architecture. It's a paradigm. It's a more of a programming paradigm. You'll be using a map reduce paradigm for big data architecture. And I will be teaching this unit next semester, FIT3142. And this unit will also be offered at the Clayton campus also. It's under David Tanier, Associate Professor David Tanier is a CE, but I'll be the lecturer for Malaysia campus. All right. So if you're interested, I hope you all can consider this unit. It's a very interesting unit. Students, when I taught this unit in semester 1, and the students who did the unit did 3143, and then they had a much more exposure to big data architecture. So they gave them a much more better experience on parallel computing on big data architecture. So it's and this unit runs on Python. Okay, it runs on Python, and we also teach you NoSQL, MongoDB. So you will learn to use Python with NoSQL, MongoDB, and then on Spark and Kafka architectures. And then your assignment, you will create an entire big data stream architecture. It's a very interesting unit. All right. So I hope you all will consider this unit as an elective for semester 1. Those of you all who are doing semester 1 next year. Those of you all in your final semester, I wish you all well. I wish you all the best as you go into the industry. There's a lot of opportunities out there. Just make sure you keep an open eye, and then you can find a lot of opportunities for you all in the future. Okay. All right. Okay. All right. So, okay. So thank you everyone. Okay. Then I will stop recording now, and then I will discuss with William a bit. So the rest of y'all, if nothing more, then y'all can leave the section already.
Okay.
Thank you very much, everyone. Thank you. It's been such a pleasure. Thank you.
Yeah. This
one second. Okay. I haven't stopped.